Hello and welcome to the final video in this series on worksheet 6. The wick in my candle, much like, the 2013 Sigur Rós album and their most recent album to date, is still burning. So we're going to do this final problem. It is on tries. You may have noticed the theme here with all of the problems on this worksheet, that being that they're all miscellaneous and very mechanical problems. I hope that these aren't too boring for you. I hope maybe you even enjoy them. We're just trying to get you some familiarity with some common data structures. These ones here in particular, tries, KD trees, are not the hottest data structures exactly. They're pretty limited usage, but we do like to get you some exposure to them. Anyway, I'm going to expect that you already know how a trie works. Basically, it's a great data structure if we want to store words, if we want to store prefixes, alphabetical things. The classic example of when you might want to use a trie is in like a Google search where you want to autocomplete search results, right? When you say like why is, and then it says the sky blue or something, that kind of thing. So basically in this example, we have a band called the Big Baller Band. And they have a bunch of members and their members' names are sorted in this trie. Okay, so the first question here is basically CEO LeVar Ball of the Big Baller Band basically wants to know who is in the band because for some reason he can't remember. So basically all this is asking you to do is just read out the trie. It wants you to say, okay, here's a trie. What are the actual words contained in the trie? So the things to remember is that we are spelling words just by descending down from the root. And the important thing here is to notice that asterisk means the end of a word specifically. Okay, so let's just see what are the elements inside of this trie. Well, there's an L, and let's just kind of go left to right. We see there's one here, LeVar. Notice that it is LeVar because the R is starred, so that's where it ends. If we go here, notice we have LaMelo because the O is starred, and we have Lonzo here. However, that's not all. There's one more, actually. There's one intermediate one, and it is just this guy over here. His name is Lame, or LeMay is probably more what they want you to say. But anyways, so notice here that this word, that LeMay, is a prefix of another name. It's a prefix of LaMelo. So the reason we know that LeMay is a separate word contained within this trie is because this node here has a little asterisk in it, right? And this, if you were to implement this in code, would probably be as simple as having a little Boolean inside a node class here that represents, that's just called, is word or something, it is true or false, right? That's how we can have tries. That's how we can have words that are prefixes of other words, and we know that they're words specifically. Notice, for example, that there is no one named, Lav, for example, in this band, because V here does not have an asterisk next to it. Okay, but yeah, first question is basically just asking you to read out the trie. This is what it is. Okay, the second question. The second question wants you to insert 2 more people into the trie. It wants you to insert LiAngelo and Love. Okay, so I'm going to go back up here. Let me erase this, and I will write out the names just so we have a little reference here. LiAngelo and Love, basically, much like the late 60s psychedelic rock group. The album Forever Changes is a real slammer. I used to listen to it a lot when I was in 7th grade. But anyways, how would we add these? So basically, we're going to traverse down the prefix tree, and once we run out of prefixes, we're going to start adding nodes. So if we want to add LiAngelo, we are going to start at L. There's an L. So then we are going to look for a node I below the L. There is no I node, so we're just going to create one, that. And then we're going to look below the I for an A node. There isn't one, so we're going to create one. Going to look for an N node. There isn't one, et cetera, et cetera. Basically, once we encounter the first node that does not exist, all subsequent nodes will not exist. We go all the way down to this O, and don't forget to put a little asterisk at this O, so we know that LiAngelo is an actual name. Notice here that even though there's an A in another part of the tree, we're not using that A because this A here that we just drew is strictly the A that is a prefix of Li. So if someone named Liam joined the band, you would put them here. And if someone named Lad joined the band, you would put them here, right? These are different A's. Don't worry about the capitalization. I don't know why there's capitalization in this problem. It doesn't really matter. Okay, and this can also lead to a theoretical question. You can begin to imagine what is the maximum number of children you could have in a node, and it's based off the size of your alphabet. Okay, so that's LiAngelo. Now, if I want to put love in, I look for the prefixes. So I start with L, here's L, I look for O, here's O, I look for V. Well, there's no V below the O, so I'm just going to add one here. And if there's no V below the O, then there's definitely going to be no E. So we just put that there. And that is basically how we would do that. Oop, and don't forget to make it a word, to mark it a word. That's basically what our tree is going to look like after this. Okay, so then some theoretical questions towards the end. How long does it take to add n words, each of max length L? So this wants you to describe this in terms of O, omega, and theta notation. So some things to note here. We are adding n words. So that means there's probably going to be an n factor in there somewhere. They're of length L, so there's going to be an L factor in somewhere. And another important thing is they're going to be maximum length L. They're not going to be strictly length L, they're going to be maximum length L. This implies an upper bound. Okay, so the amount of time it takes, you might be able to figure out, is O of NL. Why? Because it takes O of L time to add each word, because notice, the most it could possibly take for us to add a word is just L time, right? If we try to add in a word, for example, like, hello, we would have to add 5 min nodes in. And actually, even if we wanted to add a word like lamp, we would still have to traverse 3 nodes before we can add in an extra p node. So pretty much, it's always going to take a linear time proportional to the length of the word that we're adding in. Okay, and if we're adding n of them, each one takes L time, that's going to give us O of NL. Why is it O of NL and why is it not theta of NL, right? Because there's no way to break early. You always have to traverse the entire length of the word every time, right? So why is it theta? Why is it not theta? And it's because of this max word. Remember that we are saying it is of maximum length L. It is not guaranteed that it is of length L. So for example, if we want to add in 10 words of length 10, this would take 100. And let's say that L in this case is equal to 10. But if we want to add 10 words, each one is of length 1, it would only take 10 times, right? We can say the maximum it could possibly take is this much, but it could take less than that. So that's why we give it an O bound, because of this max thing. This is something you might see a lot. If you ever see something about adding like a string or something and it's a maximum length L, that usually implies an O bound because you don't know the exact length. Okay, a related question, what is the best case and worst case runtime to check whether a word of length L is in a trie? Okay, well, what's the best case? So the best case is going to be just constant time. What is that case going to be? Well, it's actually just the case that the first letter of the word is not in the trie, right? If you go back up to this trie and I were to ask you, hey, is the word, let's look up a name. Hey, is, Xenophon, the ancient Greek historian who finished Thucydides' work during the plague of Athens after Thucydides died, is he in the tree? The answer is no, and you can tell right at the first letter because we only start with X, we don't start with L, right? So you can instantly return no, basically. So that would give us a constant time runtime. And then what is the worst case runtime? Well, the worst case is actually when the word of length L is in the trie, because then you have to verify, you have to go down and say, hey, is LiAngelo, for example, in the tree? You have to verify, yes, L is here, I is here, A is here, N, G, L, E, O. You have to go all the way down to LiAngelo, which could be as long as the tree is possible, and you have to verify that. So that's going to take L time. In the worst case, it is a theta L. Why is this one theta and not O? Because earlier I just said, okay, well, if the word is maximum length L, that doesn't necessarily mean it is length L. So that's why I gave it this question an upper bound of O. Why is this one theta? And that's because we're talking about the worst case, right? One way you can imagine it is that if you were to, for example, search for a word that was anything less than L, let's say if the maximum length is L, you're searching for a word that is a shorter word, well, that by definition is not the worst case because it's not the longest word you could possibly search, right? In other words, the worst case is only when you are searching a word that is exactly length L, the longest possible. That's why it's theta, because if it was any less so, it would be the worst case by definition. Similarly, if it was any longer, well, then that would be the worst case, and this would not be the worst case. Okay, I hope that made some sense. That is the end of this worksheet, and I hope that's a decent introduction to some of these data structures.